Close your eyes and imagine a question that has haunted humanity since we first looked up at the stars. Are we alone? In the vast expanse of the cosmos, among trillions of stars and countless worlds, is Earth the only planet where life emerged? Or is the universe teeming with life, waiting to be discovered? For most of history, we could only wonder. The planets beyond Earth were distant points of light, their nature unknown. But in recent decades, our understanding has transformed dramatically. We've discovered thousands of planets orbiting other stars, exoplanets, and found that worlds are common, perhaps numbering in the billions in our galaxy alone. Tonight, we'll explore the planets and moons where life might exist. Not science fiction fantasies, but real worlds identified by telescopes and space probes, places where conditions could just possibly support biology. We'll journey to planets orbiting distant stars in their habitable zones, where liquid water might flow. We'll visit moons in our own solar system, hiding vast oceans beneath icy shells. We'll examine what scientists look for when searching for life biosignatures in atmospheres, chemical imbalances that hint at metabolism. This is the story of astrobiology, the search for life beyond Earth. It's a tale of careful observation, cautious optimism, and the recognition that life, if it exists elsewhere, might be utterly unlike anything we've imagined. Before searching for life, we must understand what makes a world habitable. Life as we know it requires certain conditions. The question is, how specific are those requirements, and could life exist under conditions radically different from Earth's? The most fundamental requirement is liquid water. All life on Earth uses water as a solvent, the medium in which biochemical reactions occur. Water has unique properties. It dissolves many substances, remains liquid over a wide temperature range, expands when frozen, allowing ice to float, insulating liquid water below, and is abundant in the universe. While other solvents, ammonia, methane, sulfuric acid, have been proposed, water remains the most likely basis for life. This focus on water defines the habitable zone, the range of orbital distances from a star where a planet's surface temperature allows liquid water to exist. Too close and water boils away. Too far and it freezes solid. Earth sits comfortably in the Sun's habitable zone at about 93 million miles. Venus, at 67 million miles, is too hot. Its surface reaches 900 degrees Fahrenheit. Mars, at 142 million miles, is too cold. Water exists mostly as ice. But habitable zones aren't simple. A planet's atmosphere profoundly affects temperature. Venus's thick CO2 atmosphere creates a runaway greenhouse effect, making it hotter than Mercury despite being farther from the Sun. Mars, with a thin atmosphere, is cold despite receiving substantial sunlight. Earth's atmosphere, nitrogen, oxygen, CO2, water vapor, maintains temperatures in a narrow range, allowing liquid water over much of the surface. Planetary mass matters. A planet needs sufficient gravity to retain an atmosphere. Too small, and atmospheric gases escape to space. Mars, about 1/10 Earth's mass, lost most of its atmosphere over billions of years, drying the surface. Too massive, and a planet becomes a gas giant with no solid surface. Jupiter and Saturn, hundreds of times Earth's mass, are balls of hydrogen and helium with no place for water-based life. Geological activity is important. Earth's interior heat drives plate tectonics, recycling carbon and regulating climate. Volcanoes release gases, replenishing the atmosphere. Without geological activity, a planet's atmosphere might disappear and climate regulation could fail. Mars lacks plate tectonics, contributing to its atmospheric loss and cold, dry surface. Magnetic fields protect atmospheres from stellar wind-charged particles from the star. Earth's magnetic field deflects solar wind, preventing atmospheric stripping. Mars lacks a strong field, allowing solar wind to gradually remove its atmosphere. For life to persist, a planet likely needs magnetic protection generated by a molten, convecting core. Stellar type influences habitability. Stars vary enormously. The Sun is a G-type star, medium-sized, stable, long-lived. Smaller M-type stars, red dwarfs, are dimmer and cooler, but far more common, making up about 75% of stars. Larger stars, F, A, B types, are brighter but short-lived, burning out in millions rather than billions of years, perhaps not giving life time to evolve. Red dwarfs present challenges. Their habitable zones are very close to the star Mercury's distance or closer. At such proximity, planets likely become tidally locked, with one side always facing the star, like the Moon facing Earth. This creates extreme temperature differences, scorching day side, freezing night side, potentially preventing liquid water. Red dwarfs also flare frequently, bathing nearby planets in radiation and stellar wind, possibly stripping atmospheres or sterilizing surfaces. Yet red dwarfs outnumber Sun-like stars, and their long lifespans, trillions of years, give life ample time to develop. If planets around red dwarfs can maintain atmospheres and redistribute heat, they might be habitable despite challenges. Chemical elements are essential. Life on Earth uses carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur-abundant elements forming complex molecules. Carbon's ability to form long chains and diverse structures makes it ideal for biological complexity, while silicon has similar properties and could theoretically substitute for carbon. It's less versatile. Most scientists expect life elsewhere to be carbon-based, using similar chemistry to Earth life. Energy sources drive life. On Earth, most life relies directly or indirectly on sunlight. Photosynthesis converts light energy into chemical energy. But not all life needs sunlight. Deep-sea hydrothermal vents host ecosystems powered by chemical energy. Bacteria oxidize hydrogen sulfide from the vents, forming the base of a food web. This chemosynthesis shows that life can exist without photosynthesis, expanding possibilities for life in dark environments like subsurface oceans. Time is crucial. Life on Earth appeared relatively quickly. Fossil evidence suggests microbes existed 3.5 to 3.8 billion years ago, just a few 100 million years after Earth formed. But complex life took far longer. Multicellular organisms appeared only about 600 million years ago, and intelligent life far more recently. If intelligent life is rare even when conditions are favorable, finding it may require searching trillions of worlds. Defining habitability involves balancing known requirements with recognition of our limited perspective. We know one example of life Earth. Extrapolating from a single data point is perilous. Life elsewhere might tolerate conditions we consider uninhabitable or require conditions we haven't considered. Our search focuses on Earth-like worlds because we understand them, not because they're the only possibility. Still, starting with water and Earth-like conditions is reasonable. Water is abundant, chemically active, and we know it works. As our search progresses and technology improves, we can broaden criteria, looking for exotic biochemistries and environments. For now, we seek worlds where water flows, atmospheres protect, and chemistry allows complexity. These are the planets where life might exist. Before 1992, we knew of only 9 planets, those in our solar system. Today, we've confirmed over 5,000 exoplanets orbiting other stars, with thousands more candidates awaiting confirmation. This explosion of discovery transformed our understanding. Planets are common, solar systems are diverse, and habitable worlds likely number in the billions. Detecting exoplanets is challenging. Even the closest stars are trillions of miles away, and planets don't emit light, they only reflect their star's light faintly. A planet next to its star looks like a firefly next to a searchlight. Direct imaging is nearly impossible, except for large planets orbiting far from dim stars. Instead, astronomers use indirect methods. The transit method watches for tiny dips in a star's brightness when a planet passes in front. If a planet's orbit is aligned edge-on from our perspective, it blocks a small fraction of starlight during transit, typically 1% or less for Earth-sized planets, more for larger worlds. By measuring these dips repeatedly over multiple transits, we confirm planets and estimate their size with remarkable precision. The geometry is straightforward, but requires patience. A planet must transit at least 3 times to confirm its orbital period. For a planet in Earth's orbit, that means observing for at least 3 years. Closer planets transit more frequently. A hot Jupiter might transit every few days, but habitable zone planets around Sun-like stars require years of continuous observation. The Kepler Space Telescope, launched in 2009, revolutionized exoplanet science. Using the transit method, Kepler discovered over 2,600 confirmed planets and identified thousands more candidates still being verified. Kepler stared at a single patch of sky containing 150,000 stars for 4 years, watching for transits with unprecedented precision. It could detect brightness changes as small as 0.01% sensitive enough to find Earth-sized planets around Sun-like stars. Kepler's discoveries revealed that small rocky planets are common throughout the galaxy. About 20–25% of Sun-like stars have rocky planets roughly Earth-sized in or near habitable zones. Extrapolating to the Milky Way's 100 to 400 billion stars suggests tens of billions of potentially habitable worlds exist in our galaxy alone. This transformed our understanding from planets might be rare to planets are everywhere. The radial velocity method, also called Doppler spectroscopy, detects planets through their gravitational effect on stars. As a planet orbits, it tugs the star slightly, causing the star to wobble in a small circle or ellipse. This wobble shifts the star's light via the Doppler effect toward blue wavelengths when the star moves toward us, toward red when moving away. By measuring these tiny wavelength shifts in the star's spectrum, astronomers infer the planet's mass and orbital characteristics. The radial velocity method was the first to reliably detect exoplanets. In 1995, Swiss astronomers Michel Mayor and Didier Queloz used radial velocity to discover 51 Pegasi b, the first confirmed exoplanet orbiting a Sun-like star. This hot Jupiter, orbiting its star every 4.2 days, shocked astronomers who expected Jupiter-sized planets only in distant, cold orbits like Jupiter's. The discovery earned Mayor and Queloz the 2019 Nobel Prize in Physics. Radial velocity measurements require extraordinary precision. Earth causes the Sun to wobble at about 0.1 meters per second, slower than walking pace. Detecting this requires measuring Doppler shifts to precisions of centimeters per second in starlight traveling trillions of miles. Modern spectrographs achieve this through careful calibration, stable temperatures, and sophisticated data analysis. Both methods have limitations and biases. Transit requires edge-on alignment. Only about 0.5% of planets transit from our viewpoint, meaning we miss most planets. Radial velocity works best for massive planets. Close to stars, they create larger, easier to detect wobbles. Small planets in wide orbits produce tiny signals that are difficult to distinguish from stellar activity. Stars have their own variability spots, flares, oscillations that can mimic or mask planetary signals. As a result, early discoveries were biased toward hot Jupiters, gas giants, orbiting very close to their stars, completing orbits in days. These worlds, with surface temperatures exceeding 1000 degrees Celsius, are scorching and completely uninhabitable. They were easy to find. Large size creates deep transits. Close orbits mean frequent transits, and massive planets near stars create large radial velocity signals. But they're not representative of most planets. As techniques improved and observation times lengthened, astronomers detected smaller, cooler planets. Statistical analysis of Kepler data revealed that small planets Earth to Neptune sized are far more common than gas giants. And many of these small planets orbit in habitable zones where temperatures might allow liquid water. Other detection methods complement transits and radial velocity. Gravitational microlensing uses a foreground star's gravity to magnify light from a background star. If the foreground star has planets, they create brief brightness spikes in the lensing event. This method can detect planets at any orbital distance, including rogue planets floating freely through space without stars. However, microlensing events are one-time occurrences. Once the alignment passes, the planet can't be studied further. Direct imaging, while challenging, is improving. Using coronagraphs or star shades to block starlight, astronomers can photograph planets directly. This works best for young, massive planets orbiting far from their stars. They're still hot from formation and emit infrared light. Direct imaging allows detailed study taking spectra to analyze atmospheric composition, but remains limited to specific types of planets. Astrometry, measuring a star's precise position over time, can detect the wobble caused by orbiting planets. This method works for massive planets in wide orbits and will become more powerful as measurements improve. The European Space Agency's Gaia mission, mapping positions of billions of stars with microarcsecond precision, will detect thousands of planets through astrometry. As detection methods mature, we're finding planets around diverse stars, red dwarfs, binary stars, white dwarf remnants. We've discovered planets in extreme environments orbiting pulsars, in dense star clusters, around evolved giant stars. This diversity shows that planet formation is robust, occurring in conditions far more varied than our solar systems. The Transiting Exoplanet Survey satellite, TESS, launched in 2018, is surveying the entire sky for transiting planets around nearby bright stars. Unlike Kepler, which observed one patch deeply, TESS observes most of the sky, finding planets close enough for detailed follow-up. TESS has discovered hundreds of planets, including many around nearby stars prime for atmospheric characterization with James Webb Space Telescope. Future missions will push detection limits further. ESA's Plato mission, launching in 2026, will search for Earth-sized planets around Sun-like stars. NASA's proposed HabEx and LUVOIR missions would directly image dozens of Earth-like planets, analyzing their atmospheres for biosignatures. Within decades, we'll have comprehensive catalogues of nearby habitable worlds, ready for the search for life. One of the most tantalizing discoveries is Proxima Centauri b, orbiting the nearest star to our solar system. Humanity's closest potential interstellar destination. Proxima Centauri, about 4.24 light-years away, is a red dwarf, small, cool, and dim compared to the Sunday. With only about 12% the Sun's mass and 0.15% its luminosity, Proxima Centauri is barely visible to the naked eye, despite being our nearest stellar neighbor. Red dwarfs like Proxima are the most common type of star, making up about 75% of all stars in the galaxy. Proxima Centauri b, discovered in 2016 using radial velocity, orbits every 11.2 days at a distance of about 4.7 million miles, 7 times closer to Proxima Centauri than Mercury is to the Sunday. Yet because Proxima Centauri is so dim, this close orbit places Proxima b squarely in the habitable zone. The planet receives about 65% of the irradiation Earth receives from the Sun, suggesting surface temperatures could be moderate if the planet has an atmosphere. Proxima b has a minimum mass about 1.27 times Earth's. Because radial velocity only provides minimum mass, the true mass depends on the orbital inclination, which is unknown. The actual mass could be somewhat higher. If Proxima b is rocky like Earth, it likely has similar size and surface gravity. The planet's proximity to its star means it's probably tidally locked, with one hemisphere permanently facing the star while the other remains in eternal night, much like the moon always shows the same face to Earth. Tidal locking creates challenges for habitability. The star-facing hemisphere would be scorching hot, while the dark hemisphere would be frozen. However, if Proxima b has a substantial atmosphere, winds could redistribute heat from the day side to the night side, moderating temperatures and potentially creating temperate regions along the terminator, the boundary between day and night. Climate models suggest that with an Earth-like atmosphere, Proxima b could maintain liquid water in certain regions. But Proxima Centauri's stellar activity poses serious challenges. Red dwarfs are magnetically active, producing frequent and powerful flares, sudden increases in brightness, accompanied by intense radiation and stellar wind. Proxima Centauri flares regularly, sometimes increasing in brightness by several times its normal luminosity. During flares, the planet receives intense ultraviolet and X-ray radiation, potentially hundreds of times stronger than Earth receives from the Sunday. This radiation could strip away Proxima b's atmosphere over time if the planet lacks a strong magnetic field. Earth's magnetic field protects our atmosphere from solar wind, deflecting charged particles that would otherwise erode the atmosphere. Whether Proxima b has a magnetic field is unknown and depends on whether the planet has a molten, convecting core, which in turn depends on the planet's internal structure, composition, and thermal history. Even if Proxima b retains an atmosphere, the intense radiation during flares could make the surface inhospitable to life. Ultraviolet radiation breaks down organic molecules and damages DNA. Life on Proxima b, if it exists, might need to shelter underground or underwater during flares, emerging only during quiet periods. Alternatively, life might have evolved defenses against radiation DNA repair mechanisms, UV-absorbing pigments, or other protective adaptations. In 2020, a second planet candidate, Proxima c, was reported at about 1.5 astronomical units, AU, from the star well outside the habitable zone in a cold orbit. Proxima c, if confirmed, would be a super-Earth or mini-Neptune with a mass several times Earth's. Its existence is still debated and awaits confirmation from additional observations. Despite uncertainties and challenges, Proxima Centauri b remains one of the most exciting exoplanet discoveries because of its proximity. At 4.24 light-years, it's the closest exoplanet in a habitable zone. While interstellar travel remains beyond current technology, Proxima Centauri is the most feasible target for humanity's first interstellar probe. The Breakthrough Starshot Initiative, funded by Silicon Valley entrepreneur Yuri Milner, proposes sending tiny, lightweight spacecraft gram-scale star chips to Proxima Centauri using powerful ground-based lasers. The lasers would push light sails attached to the spacecraft, accelerating them to 20% of light speed. At that velocity, the probes could reach Proxima Centauri in about 20 to 30 years, sending back images and data via laser communication. This concept faces enormous technical challenges building spacecraft that can survive decades in interstellar space. developing lasers powerful enough to accelerate them, and receiving signals across 4.24 light-years. But it's not impossible. If successful, Starshot could provide close-up images of Proxima Centauri b within our lifetimes, potentially revealing whether the planet is Earth-like or barren, whether it has oceans or deserts, whether it shows any signs of life. Proxima Centauri b embodies both the promise and uncertainty of exoplanet science. It's close, it's in the habitable zone, and it might have conditions suitable for life. But it orbits a type of star very different from the Sun, faces challenges Earth doesn't experience, and might be nothing like Earth despite superficial similarities. Only further observations, and perhaps eventually direct exploration, will reveal its true nature. TRAPPIST-1, located about 40 light-years away in the constellation Aquarius, is one of the most remarkable planetary systems ever discovered. This ultra-cool red dwarf, even smaller and dimmer than Proxima Centauri, only about 9% the Sun's mass and 0.05%. Its luminosity is surrounded by 7 Earth-sized planets, packed into orbits closer than Mercury's orbit around the Sun. Discovered between 2015 and 2017 through transit observations, the TRAPPIST-1 system amazed astronomers with its configuration. All 7 planets orbit their star in nearly circular, coplanar orbits within 6 million miles of the star. The innermost planet, TRAPPIST-1b, orbits every 1.5 days. The outermost, TRAPPIST-1r, orbits every 18.8 days. For comparison, Mercury orbits the Sun every 88 days at a distance of 36 million miles. Yet, because TRAPPIST-1 is so dim and cool surface temperature, only about 2,500 K, compared to the Sun's 5,800 K. Several of these tightly packed planets receive the right amount of stellar energy for liquid water. 3 planets, TRAPPIST-1, E, F, and G, orbit in the habitable zone, and possibly a 4th, TRAPPIST-1d, sits at the inner edge. The planets are similar in size to Earth, with radii ranging from 0.77 to 1.13 times Earth's radius. Detailed transit observations during planetary transits, when planets pass in front of each other as seen from Earth, allowed astronomers to measure planetary masses through gravitational interactions. Mass measurements revealed that the planets have densities consistent with rocky composition, similar to Earth and Venus. Though some might have significant water content, potentially water worlds with deep global oceans. TRAPPIST-1e is perhaps the most Earth-like. It receives about as much stellar energy as Earth receives from the Sun, about 662 watts per square meter, compared to Earth's 1,361. With a radius about 0.92 times Earth's and mass about 0.69 times Earth's, TRAPPIST-1e could have a rocky surface, a substantial atmosphere, and liquid water oceans. Climate models suggest it might have conditions similar to Earth, depending on atmospheric composition. TRAPPIST-1, F and G, farther from the star, are cooler. TRAPPIST-1F receives about 380 watts per square meter, comparable to Mars's irradiation. TRAPPIST 1 gram receives only 129 watts per square meter. These planets would be cooler than Earth, possibly resembling ice-covered worlds. However, with greenhouse gases like CO2 or methane, they might maintain pockets of liquid water beneath ice sheets or in subsurface oceans heated by tidal forces. The system's compact configuration creates strong tidal interactions. The planet's close orbits and mutual gravitational influences generate tidal heating, the same process that keeps Europa's and Enceladus's oceans liquid. This tidal heating might help maintain habitable conditions on TRAPPIST-1 planets, providing internal heat sources independent of stellar radiation. All TRAPPIST-1 planets are almost certainly tidally locked, with one hemisphere permanently facing the star. This creates day sides and night sides with extreme temperature differences. However, atmospheric circulation could redistribute heat, and life might thrive in twilight zones along the terminator where temperatures are moderate. TRAPPIST-1's age, estimated at 7.6 billion years, is older than the Sun's 4.6 billion years. This means the planets have had ample time for life to emerge and evolve, assuming conditions were favorable. If life arose on even one of the habitable zone planets, it had billions of years to develop, potentially reaching complexity. However, TRAPPIST-1, like most red dwarfs, is magnetically active and flares frequently. Early in the system's history, the star likely experienced even more intense flares, potentially stripping planetary atmospheres. Whether the planet's retained atmospheres depends on atmospheric replenishment from volcanism, comets, or outgassing, and on magnetic field protection. The TRAPPIST-1 system is a prime target for atmospheric characterization with the James Webb Space Telescope. Webb is observing multiple planets, measuring transmission spectra as planets transit the star. Early observations of TRAPPIST-1b and c found no evidence of thick hydrogen-rich atmospheres, suggesting they might lack substantial atmospheres or have thin rocky planet atmospheres. Observations of TRAPPIST-1e, f, and g are ongoing and might reveal water vapor, CO2, methane, or other atmospheric gases. If biosignatures are detected in any TRAPPIST-1 planet's atmosphere, oxygen and methane together, for example, it would be extraordinary. The system's proximity 40 light-years is close in astronomical terms, and favorable orientation for transits make it one of the best systems for finding signs of life. With 3 potentially habitable planets, the odds are improved if habitability is common but life is rare. Having multiple chances increases the probability of detection. TRAPPIST-1 also illustrates the importance of exploring diversity. The system is utterly unlike our solar system. 7 rocky planets orbiting a star far smaller and cooler than the Sun, all closer to their star than Mercury. Yet, the physics of habitability, liquid water, moderate temperatures, atmospheric protection still apply. Life, if it exists there, would experience conditions profoundly different from Earth, perhaps a dim red sun hanging motionless in the sky, no day-night cycle, no seasons, just perpetual twilight or eternal noon depending on location. Yet life might adapt to such conditions as it has adapted to Earth's extremes. Kepler 452b, about 1,400 light-years away, orbits a Sun-like star in a 385-day orbit, nearly identical to Earth's year. The planet is about 60% larger than Earth and receives similar sunlight. This Earth's cousin might be rocky or a water world, depending on composition. Its star, slightly older and brighter than the Sun, has supported stable conditions for over 6 billion years, more than enough time for life to evolve. Unfortunately, Kepler 452b is too distant for detailed study with current technology. We know its size and orbit, but not its mass, composition, or whether it has an atmosphere. It remains a tantalizing mystery, a world that could be remarkably Earth-like or utterly different. LHS 1140b, about 40 light-years away, is a super-Earth 1.7 times Earth's radius, 6 times its mass, orbiting a red dwarf every 25 days. It sits in the habitable zone, receiving about half the light Earth gets. Models suggest it could be a rocky planet with a dense atmosphere, possibly retaining liquid water despite its star's flares. LHS 1140b's star is quieter than most red dwarfs, flaring less frequently. This improves habitability prospects. The planet transits its star, allowing atmospheric studies. Early observations detected hydrogen, suggesting a thick atmosphere. Further studies will search for water vapor, oxygen, or methane gases that could indicate habitability or life. K218b, about 120 light-years away, made headlines in 2019 when water vapor was detected in its atmosphere, the first time water was found on a habitable zone exoplanet. A super-Earth about 2.7 times Earth's radius and 8.6 times its mass, K218b, orbits a red dwarf every 33 days. But K218b's habitability is uncertain. It's likely a mini-Neptune, a small gas planet with a hydrogen-helium envelope, and possibly a water-rich core. The surface might be inhospitable, a deep, high-pressure ocean beneath a thick hydrogen atmosphere, perhaps with no solid surface. Or it could be a water world with surface oceans, depending on the hydrogen envelope's thickness. Future observations will clarify K218b's nature and whether it's truly habitable. Dozens more potentially habitable exoplanets have been discovered, and thousands of candidates await confirmation. Kepler's data suggest that about 20–25% of Sun-like stars have rocky planets in habitable zones. The Milky Way contains 100 to 400 billion stars, implying tens of billions of potentially habitable worlds in our galaxy alone. Most known exoplanets orbit stars within a few hundred light-years. These are our local neighborhood in a galaxy 100,000 light-years across. As telescopes improve and surveys continue, we'll find Earth-like planets around nearby stars, close enough for detailed study. The discovery of life, if it exists, might come from analyzing an exoplanet's atmosphere and finding biosignatures, chemical evidence of biology. The diversity of exoplanets is astounding. We've found worlds made of diamond, planets orbiting binary stars, gas giants orbiting closer than Mercury, rocky planets far larger than Earth, and systems packed with planets in resonant orbits. This diversity suggests that whatever we imagine, nature has likely created. Somewhere among these worlds, conditions conducive to life almost certainly exist. Finding them is the challenge. Discovering a habitable planet isn't the same as finding life. A world might have liquid water and a stable climate, yet remain barren. To detect life, we need biosignatures, observable indicators that biological processes are occurring. On Earth, life profoundly affects the atmosphere. Oxygen makes up 21% of our air, but oxygen is highly reactive. It binds to rocks, metals, and organic matter, removing itself from the atmosphere. Without constant replenishment, atmospheric oxygen would disappear in millions of years. On Earth, photosynthetic organisms, plants, algae, cyanobacteria produce oxygen, maintaining its abundance. Atmospheric oxygen is thus a biosignature indicating life. But oxygen alone isn't conclusive. Some non-biological processes can produce oxygen. Ultraviolet light splits water molecules in the upper atmosphere, releasing oxygen. On a planet with abundant water and strong UV from a young or active star, oxygen might accumulate without life. To confidently identify life, scientists look for chemical combinations unlikely to coexist without biology. Oxygen and methane together are a strong biosignature. Methane, CH4, is unstable in oxygen-rich atmospheres. It oxidizes quickly. On Earth, methane exists because organisms continually produce it. Bacteria in wetlands, digestive tracts, termite mounds. If a planet's atmosphere contains both oxygen and methane, something must be replenishing methane despite its reaction with oxygen. Biology is the most plausible explanation. Other biosignatures include phosphine, pH3, dimethyl sulfide, DMS, and nitrous oxide, N2O. These gases are produced by life on Earth and react quickly with atmospheric oxygen, or UV light, so their presence suggests ongoing production. Phosphine, in particular, is difficult to produce non-biologically, making it a promising biosignature. In 2020, scientists reported detecting phosphine in Venus's atmosphere. If confirmed, this would be extraordinary. Venus is infernally hot, with surface temperatures around 900 degrees Fahrenheit and sulfuric acid clouds. But high in Venus's atmosphere, temperatures are Earth-like, and some scientists speculate that airborne microbes could exist. The phosphine detection is controversial. Other teams couldn't confirm it, and non-biological sources might explain the signal. But it illustrates how unexpected biosignatures might appear. Detecting biosignatures on exoplanets requires analyzing their atmospheres. When an exoplanet transits its star, some starlight passes through the planet's atmosphere before reaching us. Different gases absorb light at specific wavelengths. By splitting starlight into a spectrum and measuring absorption, we identify atmospheric gases, a technique called transmission spectroscopy. This is incredibly challenging. The planet's atmosphere is a thin shell, and only a tiny fraction of starlight passes through it. Signals are faint, requiring large telescopes and precise instruments. The James Webb Space Telescope, with its large mirror and infrared sensors, is designed for this task. It's currently studying exoplanet atmospheres, searching for water vapor, CO2, methane, and potentially biosignatures. Future telescopes will improve sensitivity. NASA's Nancy Grace Roman Space Telescope and the European Extremely Large Telescope will detect smaller planets and fainter signals. The proposed HabEx and LUVOIR missions would use coronagraphs or starshades to block starlight, directly imaging exoplanets and analyzing their atmospheres. These missions could detect biosignatures on dozens of Earth-like worlds within decades. But interpreting biosignatures is complex. Atmospheres are influenced by geology, stellar activity, and chemistry. A signal that looks like life might have non-biological explanations. Confirming life requires multiple lines of evidence, multiple biosignatures, atmospheric chemical imbalances, and perhaps surface features suggesting biology. One proposed biosignature is the vegetation red edge, a sharp increase in reflectivity at near-infrared wavelengths caused by chlorophyll in plants. On Earth, vegetation reflects infrared light, creating a distinctive spectrum. If an exoplanet's surface shows this signature, it might indicate photosynthetic life. But non-biological minerals can create similar spectra, and alien photosynthesizers might use different pigments, producing different signals. Seasonal variations could indicate life. On Earth, atmospheric CO2 fluctuates seasonally. Plants absorb CO2 during growth and release it when decaying. An exoplanet showing similar cycles might have seasonal biology. But geological processes, volcanism, ocean chemistry can also cause cycles, complicating interpretation. Technosignatures, evidence of technology, are another approach. Radio signals, laser pulses, or atmospheric pollutants from industry could indicate intelligent life. The search for extraterrestrial intelligence, SETI, scans radio frequencies for artificial signals. Detecting industrial pollutants, CFCs, nitrogen dioxide in exoplanet atmospheres would suggest technological civilization. However, technosignatures are speculative. Intelligent life might be rare, use communication methods we don't recognize, or exist briefly before self-destructing. Focusing on biosignatures from simple life microbes, algae might be more productive, since microbial life likely vastly outnumbers intelligent life. Time is a factor. Light from distant planets takes years to centuries to reach us. If we detect a biosignature from a planet 1,000 light-years away, we're seeing life as it existed 1,000 years ago. That life might now be extinct, or it might have evolved. We're observing the past, limited by light speed. False positives are possible. Non-biological processes might mimic biosignatures, volcanic gases, atmospheric chemistry, stellar flares all can create signals resembling life. Distinguishing biology from geology requires careful analysis, multiple observations, and corroborating evidence. Despite challenges, detecting biosignatures is within reach. Thousands of exoplanets are known, and technology for atmospheric analysis is advancing rapidly. Within this century, we might detect gases in an exoplanet's atmosphere that strongly suggest life. The discovery would be tentative, requiring confirmation and ruling out alternatives, but it could mark humanity's first detection of life beyond Earth. Even finding habitable worlds without biosignatures is valuable. Knowing that Earth-like planets exist with water and stable climates narrows the search and guides future missions. Each planet studied teaches us about habitability and planetary evolution, informing the search for life. The absence of biosignatures would also be significant. If we study dozens of habitable planets and find no signs of life, it suggests life is rare, even on worlds with favorable conditions. This would inform our understanding of life's origin and encourage us to protect Earth's biosphere, perhaps the only life in a vast, empty cosmos. While exoplanets capture attention, some of the most promising places to search for life are closer moons in our own solar system. Several moons of Jupiter and Saturn hide vast oceans beneath icy shells, heated by tidal forces rather than sunlight. These worlds, dark and cold on their surfaces, might harbor life in their liquid interiors. Europa, Jupiter's fourth largest moon, has fascinated scientists for decades. Slightly smaller than Earth's moon, Europa is covered in ice, a smooth, cracked surface with few craters, indicating geological activity. Beneath this ice lies an ocean 40 to 100 miles deep, containing more water than all of Earth's oceans combined. How do we know? Several lines of evidence. Galileo spacecraft observations in the 1990s revealed Europa's magnetic field behavior, consistent with a conductive liquid, salty water, beneath the surface. Images show chaos terrain regions where the ice appears to have melted, refrozen, and fractured, suggesting heat from below, and the surface's smoothness indicates recent resurfacing, erasing old craters. Europa's ocean exists because of tidal heating. Europa orbits Jupiter in a slightly elliptical orbit. As Europa moves closer and farther from Jupiter, the giant planet's gravity stretches and compresses the Moon, generating heat through friction, like bending a wire back and forth until it heats up. This tidal heating keeps Europa's interior warm enough to maintain a liquid ocean despite being far from the Sunday. Could life exist in Europa's ocean? On Earth, hydrothermal vents on the seafloor support ecosystems independent of sunlight. Bacteria oxidize chemicals from the vents, and diverse organisms, tubeworms, crabs, fish thrive in total darkness. If Europa's ocean floor has similar vents, it could host life. Europa's ocean likely contacts rocky seafloor, where water-rock interactions might produce hydrogen, methane, and other chemicals useful for life. Tidal heating might drive hydrothermal activity, creating environments analogous to Earth's deep-sea vents. If life originated in such environments on Earth, similar conditions on Europa could support life. Challenges include energy. Without sunlight, Europa's biosphere would rely entirely on chemical energy, either from hydrothermal vents or from chemicals delivered from the surface. Radiation from Jupiter bombards Europa's surface, splitting water ice into hydrogen and oxygen. If these chemicals reach the ocean, they might provide energy for life, though transporting surface chemicals through miles of ice is difficult. NASA's Europa Clipper mission, launching in 2024, will study Europa in detail, conducting dozens of close flybys. It will map the ice thickness, analyze surface composition, and search for water plumes. Hubble Space Telescope observations suggest Europa sometimes ejects water into space, plumes that might allow sampling the ocean without landing. Europa Clipper might fly through a plume, analyzing water chemistry for signs of life. Future missions might land on Europa and drill through the ice to the ocean below. This is technologically challenging. The ice is miles thick, and drilling in cold, remote environments is difficult. But robotic submarines could explore Europa's ocean, searching for life directly. Such missions are decades away, but represent the ultimate goal: directly sampling an alien ocean for biology. Enceladus, a small moon of Saturn, surprised scientists with geysers of water erupting from its south pole. Cassini spacecraft observations confirmed Enceladus has a subsurface ocean, likely global, beneath an icy shell averaging 12 to 15 miles thick. Tidal heating from Saturn keeps the ocean liquid. Enceladus's geysers are extraordinary. Jets of water vapor and ice particles spray from fractures in the south polar region, creating a plume visible from space. Cassini flew through the plume multiple times, analyzing its composition. It found water, salts, organic molecules, carbon-based compounds, and molecular hydrogen ingredients, suggesting hydrothermal activity on the ocean floor. Molecular hydrogen, H2, is particularly significant. On Earth, certain microbes metabolize hydrogen, combining it with CO2 to produce methane and energy, a process called methanogenesis. Enceladus's plume contains hydrogen, indicating reactions between water and hot rock, producing hydrogen and other chemicals. If microbes exist in Enceladus's ocean, they might use hydrogen for energy. Cassini also detected complex organic molecules in the plume compounds with dozens of carbon atoms. While organics form non-biologically, their presence indicates chemical complexity, a prerequisite for life. Together, the evidence, liquid water, energy sources, organic molecules, suggests Enceladus meets key habitability criteria. Enceladus's plume allows sampling the ocean without landing. A future mission could fly through the plume, collecting particles and analyzing them for biological signatures, amino acids, lipids, or metabolic byproducts. This is less invasive than drilling and could confirm whether Enceladus harbors life. Titan, Saturn's largest moon, is unique. It has a thick atmosphere denser than Earth's, composed mostly of nitrogen, with methane and organic haze. Titan's surface temperature is about -290 degrees Fahrenheit, -179 degrees Celsius, cold enough that water ice is rock hard and methane behaves like water, existing as liquid, clouds, and rain. Titan has lakes and seas of liquid methane and ethane, the only world besides Earth with stable surface liquids. Rivers carved by methane rain flow into lakes, creating a hydrological cycle analogous to Earth's water cycle. Titan's surface is covered in organic compounds, tholins, produced by UV light and charged particles breaking down methane and nitrogen in the atmosphere. Beneath Titan's icy crust lies a subsurface ocean of liquid water, detected by Cassini through gravitational measurements. This ocean, perhaps 60 miles deep, exists 30 to 60 miles below the surface, heated by tidal forces and radioactive decay. Life might exist in this ocean, though isolated from the surface by thick ice. But Titan's surface environment is also intriguing. Could life use liquid methane as a solvent instead of water? At Titan's temperature, water is frozen solid, but methane is liquid. Hypothetically, methanogenic life could metabolize in methane using different chemistry than water-based life. This is speculative. No evidence suggests such life exists, but Titan's unique environment invites imagination. NASA's Dragonfly mission, launching in 2027, will send a rotorcraft to explore Titan. Dragonfly will fly across Titan's surface, landing at multiple sites to study chemistry, geology, and organic compounds. It will investigate whether Titan's chemistry could support life, though detecting life directly is unlikely without sampling the subsurface ocean. Ganymede and Callisto, also moons of Jupiter, likely have subsurface oceans. Ganymede, the solar system's largest moon, has a salty ocean beneath 90 miles of ice, detected through magnetic field observations. Callisto, farther from Jupiter, might have an ocean beneath 120 miles of ice. Both moons receive less tidal heating than Europa, so their oceans might be colder and less active, reducing habitability prospects. Still, they add to the list of ocean worlds warranting future exploration. The discovery of multiple ocean worlds in the outer solar system was unexpected. Before Europa's ocean was suspected, scientists assumed life required Earth-like conditions: sunlight, surface water, moderate temperatures. Ocean worlds show life could exist in dark, cold environments, hidden beneath ice, powered by geothermal energy. This expands habitability concepts and suggests that ocean worlds might be common throughout the galaxy. If moons in our solar system have oceans, moons around exoplanets might too. Gas giants in habitable zones could host moons with surface water, warmed by the giant planet's reflected light and tidal heating. These exomoons are difficult to detect with current technology, but future missions might find them, adding countless potential habitats to the search for life. Exploring ocean worlds is a priority for astrobiology. Unlike distant exoplanets, Europa and Enceladus are reachable with current technology. Missions there could directly sample alien oceans within this century, answering the question, is life limited to Earth, or does it arise wherever conditions allow? Mars, our planetary neighbor, has been humanity's focus for life search efforts since the 19th century. Closer than the gas giant's moons and more Earth-like than Venus, Mars is accessible and tantalizingly ambiguous, perhaps once habitable, perhaps still harboring microbial life underground. Mars today is cold and dry. Surface temperatures average -80 degrees Fahrenheit, -60 degrees Celsius, ranging from -195 degrees Fahrenheit at the poles in winter to 70 degrees Fahrenheit at the equator in summer. The atmosphere is thin, less than 1% Earth's pressure, and composed mostly of CO2. Liquid water can't exist stably on the surface. It either freezes or boils away in the low pressure. But Mars wasn't always like this. Evidence from rovers, orbiters, and landers reveals that ancient Mars 3 to 4 billion years ago was wetter and warmer. Valleys carved by flowing water, ancient lake beds, minerals that form in water all indicate that liquid water once flowed on Mars's surface. The atmosphere was thicker, greenhouse warming kept temperatures higher, and rain might have fallen. This ancient Mars was potentially habitable. If life arose on Earth 3.5 to 3.8 billion years ago, it might have arisen on Mars during the same period, when conditions were similar. The question is whether Martian life survived Mars's transformation into a cold desert or went extinct as the planet dried out. Mars lost its atmosphere gradually through multiple processes. Unlike Earth, Mars lacks a strong global magnetic field today, though evidence suggests it had one early in its history. Ancient magnetized rocks in the Martian crust, detected by orbiting spacecraft, reveal that Mars once had a dynamo-generated magnetic field similar to Earth's. But around 4 billion years ago, Mars's interior cooled, the dynamo shut down, and the magnetic field collapsed. Without magnetic protection, solar wind, the stream of charged particles from the Sun, directly interacted with Mars's upper atmosphere. Over hundreds of millions of years, solar wind stripped away atmospheric gases, particularly lighter elements like hydrogen. NASA's MAVEN Mars Atmosphere and Volatile Evolution Orbiter, studying Mars's upper atmosphere since 2014, has directly measured ongoing atmospheric loss to solar wind. The process continues today, though at reduced rates now that most atmosphere is gone. Loss mechanisms include sputtering, where energetic particles from solar wind knock atmospheric atoms into space, and photochemical escape, where UV light breaks molecules apart, releasing atoms with enough energy to escape Mars's gravity. Additionally, large asteroid impacts early in Mars's history might have blasted away significant amounts of atmosphere in sudden catastrophic events. As atmospheric pressure dropped, Mars's climate transformed. Water that once flowed on the surface evaporated or froze, lakes and rivers dried up. The planet became the cold desert we see today, with average surface temperatures around -80 degrees Fahrenheit, -60 degrees Celsius, and a thin CO2 atmosphere that provides almost no greenhouse warming or protection from radiation. Yet the story is more complex than simple atmospheric loss. Geological evidence suggests Mars's climate varied over time, with periodic warm, wet periods alternating with cold, dry conditions. Orbital variations, changes in Mars's axial tilt and orbital eccentricity over hundreds of thousands to millions of years, alter how much sunlight different regions receive. When tilt is high, polar ice caps partially sublimate, thickening the atmosphere and possibly creating brief warm periods when liquid water flows. These climate cycles, if they occur, might have allowed liquid water to exist episodically throughout Martian history, not just in the distant past. Recent features that appear to be carved by flowing water gullies on crater walls, channels on hillsides might have formed during recent warm periods, perhaps within the last few million years. If so, Mars might not be permanently dry, but rather in a cold phase of a long-term cycle. Subsurface water is key to modern habitability. Liquid water almost certainly cannot exist stably on Mars's surface under current conditions. Low pressure and cold temperatures mean water either freezes or sublimates directly to vapor. But below the surface, pressure increases and geothermal heat warms the ground. Models suggest that at depths of perhaps 1 to 5 kilometers, conditions might allow liquid water, particularly brines with dissolved salts that lower the freezing point. Evidence for subsurface water includes radar observations from Mars Express and Mars Reconnaissance Orbiter showing possible liquid water beneath Mars's south polar ice cap. In 2018, radar data revealed a bright reflection beneath 1.5 kilometers of ice, interpreted as a lake of briny water kept liquid by salts and pressure. However, this interpretation is debated. Alternative explanations involving frozen clays or other materials might explain the radar signature. Recurring slope lineae, RSL, dark streaks appearing seasonally on Martian slopes, were once thought to be flowing brines. However, further study suggests they might be dry granular flows, avalanches of dry sand and dust triggered by CO2 frost sublimation rather than liquid water. The debate illustrates how difficult it is to interpret remote observations and how ambiguous the evidence for present-day liquid water remains. If liquid water exists underground, it could harbor microbial life. On Earth, the deep biosphere, microbes living kilometers below the surface in rock pores and fractures, comprises a substantial fraction of Earth's total biomass. These microbes metabolize minerals, hydrogen, and other chemicals, surviving without sunlight in completely dark environments. Similar life could exist in Martian subsurface aquifers, isolated from the harsh surface, persisting for billions of years since Mars's wet past. Detecting subsurface life requires drilling. Current Mars rovers drill only a few centimeters deep enough to sample rocks but not to reach groundwater. Future missions might drill meters to hundreds of meters, searching for water and potential biosignatures. ESA's Rosalind Franklin rover, part of the ExoMars program, was designed to drill up to 2 meters deep, collecting samples protected from surface radiation and accessing material where organic molecules might be preserved. However, the mission has faced delays, and its future is uncertain following geopolitical changes. Mars Sample Return, a joint NASA-ESA mission, aims to bring Perseverance rover's collected samples to Earth for detailed laboratory analysis. Perseverance has been collecting rock cores from Jezero Crater, an ancient lakebed where water once flowed and might have supported microbial life. These samples, sealed in tubes and cached on Mars, will be retrieved by a future Fetch rover, launched to orbit, and returned to Earth, possibly arriving in the 2030s. Analyzing samples in Earth laboratories allows investigations impossible with rover instruments, sensitive searches for organic molecules, isotopic analysis revealing biological processes, examination of mineral textures for fossil evidence. If Martian life ever existed, even if now extinct, traces might remain in ancient rocks. Finding fossilized microbes or clear biosignatures would confirm that life arose independently on Mars, demonstrating that abiogenesis occurs when conditions allow and implying life is common throughout the universe. Curiosity and Perseverance rovers, exploring Mars since 2012 and 2021, respectively, have found organic molecules, carbon-based compounds in Martian rocks. Organics aren't direct evidence of life, they form non-biologically too, but their presence shows Mars has the chemical ingredients for life. Perseverance is collecting rock samples for future return to Earth, where sensitive laboratory analysis might detect biosignatures ancient or contemporary. Mars's subsurface is largely unexplored. Rovers and landers study the surface, but drilling technology limits depth to a few meters. To explore deep underground, future missions might use drills capable of reaching hundreds of meters or kilometers, searching for aquifers and potential life. Methane detections complicate Mars's story. Several times, orbiters and rovers have detected small amounts of methane in Mars's atmosphere. Methane is unstable. UV light breaks it down within a few centuries. Its presence suggests active sources, either geological serpentinization, water reacting with rock, or biological microbes producing methane as a metabolic byproduct. But methane observations are inconsistent. Sometimes it's detected, sometimes not. Concentrations vary seasonally and geographically. Whether Mars has sustained methane emission or occasional bursts is unclear. The ExoMars Trace Gas Orbiter, designed to measure methane precisely, has detected little or none, deepening the mystery. If methane exists, identifying its source is critical. Biological methane would indicate life. Geological methane would reveal active chemistry. Understanding Mars's methane, if it exists, is a major astrobiology goal. Mars's surface is bombarded by UV radiation and oxidizing chemicals. Perchlorate's highly reactive compounds pervade Martian soil, destroying organic molecules. Viking landers in the 1976 conducted biology experiments, finding ambiguous results. One experiment suggested biological activity, but perchlorates might have caused false positives. Consensus holds that Viking didn't detect life, but the question remains open. Future missions aim to clarify. NASA's Mars Sample Return mission will bring Perseverance's samples to Earth for detailed analysis. European Space Agency's ExoMars rover, delayed multiple times, will drill up to 2 meters deep, searching for organics protected from surface radiation. These missions might finally answer whether Mars hosts life. Mars also offers lessons for exoplanet habitability. Understanding why Mars lost its atmosphere and water informs models of how exoplanets evolve. If Mars was once habitable but became barren, other planets might follow similar paths, making long-term habitability rare, even where conditions initially favor life. Despite uncertainties, Mars remains the most accessible world where life might exist. It's close enough for detailed study and eventual human exploration. If life exists or once existed, Mars offers the best chance of finding it within our lifetime. Venus, Earth's sister planet, is a world of extremes. Surface temperatures reach 900 degrees Fahrenheit, 475 degrees Celsius, hot enough to melt lead. Atmospheric pressure is 90 times Earth's equivalent to being 3,000 feet underwater. The atmosphere, 96% CO2 with clouds of sulfuric acid, creates a runaway greenhouse effect. Venus is the solar system's most hellish world, seemingly inimical to life. Yet Venus wasn't always this way. Models suggest that billions of years ago, Venus might have had liquid water oceans and moderate temperatures. Venus receives about twice Earth's sunlight, but if it had oceans and a thinner atmosphere, it could have maintained habitable surface conditions for hundreds of millions to a billion years. What happened? Gradual evaporation of oceans created water vapor, a powerful greenhouse gas in the atmosphere. This increased temperature, evaporating more water in a feedback loop. Eventually, all water evaporated, and UV light split water molecules, releasing hydrogen to space. With no water to sequester CO2 on Earth, CO2 dissolves in oceans and is locked into rocks. CO2 accumulated, creating the current inferno. If early Venus had oceans, it might have hosted life. That life would have gone extinct as the planet heated, but fossils or chemical signatures might remain on the surface if we could reach them. Venus's surface is inhospitable to landers. Extreme heat and pressure destroy spacecraft within hours. Soviet Venera landers in the 1970s and 1980s survived only briefly, sending back images and data before succumbing. But Venus's atmosphere is intriguing. About 30 to 40 miles above the surface, conditions moderate. Temperature is Earth-like to 70 degrees Fahrenheit. Pressure is similar to Earth's surface, and sunlight provides energy. This habitable zone in the clouds is where some scientists speculate life might exist. Life in Venus's clouds sounds absurd, but on Earth, microbes thrive in atmospheric water droplets. Some bacteria, algae, and fungi are lifted by winds into the upper atmosphere, remaining aloft for days or weeks. If similar organisms evolved on Venus when it had oceans, they might have adapted to the clouds as the surface became uninhabitable, evolving into airborne microbes that never touch the ground. Challenges are immense. Venus's clouds contain sulfuric acid concentrated enough to dissolve metals. Any life would need extraordinary acid tolerance. The clouds' dry water content is low, and maintaining a population in the clouds requires organisms to stay aloft indefinitely, avoiding falling to the surface or drifting into space. This might involve forming spores that survive descent to cooler atmospheric layers before being lofted back up by convection. In 2020, scientists reported detecting phosphine in Venus's atmosphere. Phosphine, pH 3, as discussed earlier, is a potential biosignature. On Earth, phosphine is produced mainly by anaerobic bacteria in oxygen-free environments. Detecting it on Venus was unexpected. If confirmed, it would suggest either life or unknown chemistry. However, the phosphine detection is controversial. Follow-up observations couldn't reliably confirm it, and some scientists argue the signal might be sulfur dioxide, so misinterpreted as phosphine due to data processing. Others propose non-biological sources, volcanism, lightning, or chemical reactions in the clouds. The debate highlights both the challenges and excitement of biosignature detection. A tentative signal provokes intense scrutiny, driving further observations and research. Whether Venus has phosphine and whether it indicates life remains unresolved, but it's directed attention to Venus's atmosphere as a potential habitat. Future missions will investigate. NASA's Da Vinci mission, launching in the 2030s, will send a probe through Venus's atmosphere, measuring composition and searching for organics. ESA's Envision orbiter will study the surface and atmosphere. These missions might clarify whether Venus's atmosphere hosts life or whether the phosphine signal was an artifact. Even if Venus lacks life, understanding it is valuable. Venus represents a runaway greenhouse, a cautionary tale for Earth as CO2 levels rise. Studying Venus's climate evolution informs our understanding of planetary habitability and the factors that determine whether a planet remains habitable or transforms into a hothouse. Venus also teaches us that habitable zones aren't fixed. Early Venus might have been habitable despite receiving more sunlight than Earth, showing that habitability depends on complex interactions between atmosphere, oceans, and geology. For exoplanets, this means the habitable zone is broader and more nuanced than simple distance from the star. Venus is unlikely to harbor life, but it's not impossible. If microbial life exists in the clouds, it would be one of nature's strangest adaptations, life in an acidic sky above a hellscape, persisting for billions of years. Finding life on Venus would revolutionize astrobiology, showing that life adapts to environments far beyond what we consider tolerable. Beyond the gas giants lie icy worlds with exotic chemistries and environments that challenge our notions of habitability. While less likely to host life than Mars or Europa, these distant moons and dwarf planets expand possibilities for where life might exist. Triton, Neptune's largest moon, is geologically active despite being one of the coldest worlds in the solar system. Surface temperatures average -390 degrees Fahrenheit, -235 degrees Celsius. Yet Voyager 2 observed geysers erupting on Triton, spewing nitrogen gas and ice particles miles into space. This activity suggests internal heat, perhaps from tidal heating or radioactive decay. Triton likely has a subsurface ocean beneath its icy shell. If so, it joins Europa and Enceladus as an ocean world. Triton's ocean would be colder and less active, but the geysers show Triton isn't geologically dead. Whether its ocean could support life is unknown. No missions are planned to study Triton in detail, but it remains a candidate for future exploration. Pluto, reclassified as a dwarf planet, surprised scientists during New Horizons' 2015 flyby. Images revealed young geological features, smooth plains, mountains, possible cryovolcanoes, indicating recent or ongoing activity. Pluto's surface is nitrogen ice, methane ice, and water ice, with a thin nitrogen atmosphere. Models suggest Pluto might have a subsurface ocean beneath its icy crust. Ammonia, detected on Pluto's surface, would lower water's freezing point, allowing an ammonia water ocean to remain liquid at Pluto's low temperatures. Radioactive decay of elements in Pluto's rocky core might provide heat, though Pluto's small size limits heating. If Pluto has an ocean, could it host life? The ocean would be extremely cold, perhaps -40 degrees Fahrenheit, -40 degrees Celsius, or colder and dark, far from the sun's energy. Chemical energy from water-rock interactions might sustain microbial life, but conditions are marginal. Pluto illustrates that even distant icy worlds might have liquid water, expanding the number of potential habitats. Ceres, the largest object in the asteroid belt, is also geologically active. Dawn spacecraft observations revealed bright spots, salt deposits left by brines that reached the surface and evaporated. Ceres likely has a briny subsurface layer or pockets of liquid water heated by radioactive decay. Ceres is small, about 600 miles across, and cold, but its water-rock interactions might produce chemical energy. Whether Ceres could host life is speculative, but it shows that habitability isn't limited to large planets or moons. Even modest bodies in the asteroid belt might have liquid water. Comets, icy bodies from the outer solar system, contain water, organics, and other volatiles. When comets approach the Sun, heating causes outgassing jets of water vapor and dust. Some scientists speculate that comets could harbor simple life, protected in icy interiors during long journeys through space. This is highly speculative, but comets deliver organics to planets, possibly seeding life or providing ingredients for its origin. Interstellar objects, asteroids, or comets from other star systems occasionally pass through our solar system. Oumuamua, detected in 2017, and Borisov, detected in 2019, are confirmed interstellar objects. Some scientists proposed Oumuamua might be artificial, a probe from another civilization, though natural explanations are more likely. Still, interstellar objects show that material travels between star systems, potentially carrying life or organics, a concept called panspermia. Panspermia proposes that life might spread between worlds via meteorites, comets, or interstellar objects. Microbes could survive in space, dormant, until landing on a new planet. If panspermia occurs, life might not originate independently on each world. It might have a common origin, spreading through the galaxy. Evidence for panspermia is limited, but meteorites from Mars have landed on Earth, and Earth meteorites have been ejected to space, potentially reaching other planets. Microbes can survive extreme conditions, radiation, cold, vacuum in dormant states. Whether they could survive interstellar travel over millions of years is uncertain, but it's not impossible. The outer solar system's exotic environments remind us that life might exist in forms we haven't imagined. Water-ammonia mixtures, methane lakes, subsurface oceans under miles of ice, all challenge the assumption that life requires Earth-like conditions. As we explore these worlds, we'll learn whether life is confined to familiar environments or adapts to the strangest places. The search for life invites big questions. How common is life? How many technological civilizations exist? And if life is common, why haven't we detected it? The Drake equation and Fermi paradox frame these questions, highlighting the uncertainties and mysteries of astrobiology. The Drake equation, formulated in 1961 by Frank Drake, estimates the number of active, communicative civilizations in the Milky Way. It's not meant to provide a definitive answer, but to structure thinking. N equals R asterisk times Fp times Ni times Fl times Phi times Fc times L, where N equals number of civilizations in our galaxy with which we could communicate. R asterisk equals rate of star formation in our galaxy. Fp equals fraction of stars with planetary systems. Ni equals number of planets per system in the habitable zone. Fl equals fraction of habitable planets where life arises. Phi equals fraction of life-bearing planets where intelligent life evolves. Fc equals fraction of intelligent civilizations that develop technology detectable across interstellar distances. L equals length of time such civilizations release detectable signals. Some factors are well constrained. R times is about 1 to 3 stars per year. Fp is close to 1. Most stars have planets. Ne is probably 0.1 to 0.5. Maybe 1 planet in 5 is in the habitable zone. But Fl, Phi, Fc, and L are unknown. Does life arise on every habitable planet, or is abiogenesis, life's origin, extremely rare? We have one example, Earth making extrapolation impossible. If life arises easily, Fl might be close to 1. If it's rare, Fl could be 0.001 or less. Does intelligent life inevitably evolve, or was Earth's path unique? Intelligence required billions of years and multiple contingent events, extinction of dinosaurs, evolution of primates, development of tools and language. Perhaps intelligence is rare even when life is common. And how long do civilizations last? Humans have had radio technology for about 100 years. If typical civilizations last only a few centuries before self-destructing or losing interest in communication, L is small, and few civilizations exist at any given time. If civilizations last millions of years, L is large, and many civilizations might coexist. Optimistic estimates, assuming life and intelligence are common, and civilizations long-lived, suggest thousands or millions of civilizations in the galaxy. Pessimistic estimates, assuming rare abiogenesis, rare intelligence, and short-lived civilizations, suggest we might be alone in the Milky Way or one of very few civilizations. This brings us to the Fermi paradox, named after physicist Enrico Fermi, who reportedly asked, "Where is everybody?" If the galaxy is billions of years old and contains billions of stars, intelligent life should have arisen many times. Some civilizations might be millions or billions of years ahead of us. They should have colonized the galaxy, leaving detectable evidence, megastructures, interstellar probes, altered star spectra. Yet we see no signs. Why? Proposed solutions to the Fermi paradox include: 1. Life is rare. Abiogenesis might require extraordinarily rare conditions. Earth's life-friendly environment, stable star, large moon, plate tectonics, magnetic field might be uncommon. If so, Habitable planets might vastly outnumber life-bearing planets. 2. Intelligence is rare. Most life might remain microbial. Complex, multicellular life took billions of years on Earth and required specific evolutionary pathways. Intelligence might be even rarer, emerging only under exceptional circumstances. 3. Civilizations self-destruct. Technology might inevitably lead to self-destruction, nuclear war, environmental collapse, AI catastrophes. If civilizations typically last only a few centuries after developing technology, they're short-lived and rare at any moment. 4. They're here but undetected. Advanced civilizations might use communication methods we don't recognize. Quantum entanglement, neutrino beams, or technologies beyond our comprehension. They might avoid contact, observing us but not revealing themselves. 5. The zoo hypothesis. Alien civilizations might deliberately avoid interfering with emerging civilizations like ours, either for ethical reasons, non-interference, or scientific reasons, observing natural development. We might be in a zoo or nature preserve. 6. Space is too vast. Interstellar travel might be impractically difficult, even for advanced civilizations. Distances between stars are immense. Light takes years to decades to reach even nearby stars. Physical travel or colonization might be economically or technologically unfeasible, limiting civilizations to their home systems. 7. We're early. Perhaps intelligent life takes billions of years to evolve, and we're among the first civilizations to arise. The universe is 13.8 billion years old, but early generations of stars lacked heavy elements necessary for planets. Sun-like stars with rocky planets became common only in recent billions of years. We might be in the first wave of intelligence. Each solution has implications. If life is rare, we're precious, and protecting Earth's biosphere becomes paramount. If civilizations self-destruct, we must avoid the same fate. If they're undetected, we should search harder, developing better detection methods. The Drake equation and Fermi paradox underscore our ignorance. We don't know how common life is, how often intelligence evolves, or how civilizations behave. Answering these questions requires exploring more worlds, detecting biosignatures, and perhaps someday encountering another civilization. For now, we continue searching, knowing each discovery, each exoplanet, each biosignature, each exploration of an ocean world brings us closer to understanding whether we're alone or part of a cosmos filled with life. We've explored worlds where life might exist, exoplanets in habitable zones, moons with subsurface oceans, Mars with its ancient rivers, Venus's acidic clouds, and exotic worlds in the outer solar system. Each is a candidate, a place where conditions might allow biology, however strange or simple. Finding life beyond Earth would be transformative. It would answer a question as old as human thought. Are we alone? The answer, whether yes or no, would reshape our understanding of life, intelligence, and our place in the universe. If we find microbial life on Mars or Europa, it would suggest life arises wherever conditions allow, implying the universe teems with microbial biospheres. If we detect biosignatures on exoplanets, it would confirm life exists around other stars, perhaps in abundance. And if we ever contact intelligent civilizations, it would mark a turning point in human history, connecting us to a galactic community. But finding nothing would be significant too. If we explore dozens of habitable worlds and find none with life, it suggests life is rare, precious, unique. This would encourage us to cherish Earth and its biosphere, perhaps the only life in a vast, empty universe. It would also raise profound questions. Why is Earth special? What conditions are necessary for life? And how often do they occur? The search for life is not just about finding aliens. It's about understanding life itself, its origins, its limits, its diversity. Studying exoplanet atmospheres, analyzing samples from Mars, exploring Europa's ocean all teach us about chemistry, geology, climate, and biology. Each mission advances our knowledge, whether or not it finds life. We're in the early stages of this search. Exoplanet discoveries began only in the 1990s. Missions to explore ocean moons are in planning or development. Techniques for detecting biosignatures are improving but still limited. Within this century, we might detect life, but we might also spend decades confirming its absence on world after world. Patience is required. Science proceeds carefully, ruling out alternatives and accumulating evidence. A single, ambiguous signal, like Venus's phosphine, invites skepticism and demands confirmation. Multiple lines of evidence, multiple biosignatures, corroborating observations, direct sampling will eventually determine whether life exists beyond Earth. Technology is advancing. Telescopes like James Webb can analyze exoplanet atmospheres in unprecedented detail. Future telescopes will study smaller, more Earth-like planets. Missions to Europa, Enceladus, and Mars will directly search for life in our solar system. Within decades, we'll have explored or studied dozens of worlds, vastly expanding our understanding. The search also inspires. Knowing that thousands of worlds exist, some perhaps harboring life, fuels curiosity and wonder. It motivates missions, funds research, and encourages collaboration across nations. The quest for life unites humanity, transcending borders and differences, focusing on a question relevant to all. As you drift towards sleep, reflect on the possibility that life exists elsewhere. Perhaps on a moon of Jupiter, microbes cluster around a hydrothermal vent in a dark ocean. Perhaps on a distant exoplanet, algae photosynthesize in an alien sea. Perhaps somewhere, intelligent beings look up at their sky, wondering if they're alone, just as we do. We don't yet know the answer, but we're searching methodically and carefully, exploring world after world. Whether we find life or not, the search itself is an adventure, revealing the diversity and beauty of the cosmos. Tomorrow, telescopes will continue observing. Rovers will continue analyzing Martian rocks. Missions will continue preparing for Europa and Enceladus. The search goes on, driven by curiosity and the hope that somewhere in the vastness of space, life exists, waiting to be discovered. Rest well, fellow traveler. The universe is vast, and its secrets are slowly unfolding. We're part of the generation searching for life beyond Earth, asking the greatest question ever posed. The answer, whatever it is, awaits in the data, the missions, the observations yet to come. Sweet dreams, knowing that among the stars there might be worlds where life flourishes, where evolution crafted creatures we've never imagined, where biology adapted to environments beyond our experience. The search continues, and one day we might find them or learn that we're alone, precious and unique, guardians of the only life in an otherwise lifeless cosmos.